Okay, so we are talking about we are doing the analysis of quicksort, and we have seen if the pivot is a good pivot, then it will partition the array into n by 2 is to n by 2. So, this is the best case. So, if our partition algorithm will partition the array into this way, then it is the best case. In that case, we have seen the recurrence is 2 t n by 2 plus theta of n, and that will give us order of n log n. So, this is the lucky case, order of n log n. And even if we see, even we have seen if this is not n by 2 is to n by 2, if it is just, if we can ensure the partition will put little fraction over here, say 1 by 10 is to 9 by 10. Okay. So, that means if the partition is n by 10 is to 9 n by 10, then we have seen this is the almost, this is referred as almost best case. Why this is also best case? Because for this we have seen the recurrence is t n by 10 plus t 9 n by 10 plus theta of n. This is the recurrence corresponding to this partition, and this will give us also order of n log n. So, this is also lucky case. Okay. So, even if one can ensure, if the partition can ensure that it will partition some little fraction guaranteed, some little fraction in one side and other side the remaining element, then also it is the lucky case. Okay. And whichever is the unlucky case, the worst case is basically 0 is to n minus 1. That means, if we choose the pivot element to be minimum or maximum. So, the worst case for quicksort is if the pivot is minimum element, minimum or maximum element from the array. In that case, the partition will be 0 is to n minus 1 if it is minimum, or n minus 1 is to 0. So, that means one sided nobody is there and another sub array is containing all the other elements. So, in that case recurrence will be t n is equal to t n minus 1 plus theta n, and this will give us the solution order of n square. So, this is the worst case, and this is we refer as unlucky case. Okay. We are unlucky if the time complexity is coming to be order of n square. So, now we will do a alternate, we will do another type of analysis. Suppose we are in our, so we have given an array. So, we call the partition algorithm. So, it is partitioning into two part. If it is good, if it is not minimum or maximum, then it will partition into not 0 is to n minus 1. So, it is a lucky case. Now, suppose in the next time we will be unlucky. So, if we have, suppose we are alternatively lucky unlucky. So, then we want to see whether eventually we will be lucky or not. So, that is the analysis we want to do. So, this is the more intuition. Suppose we alternately lucky unlucky. So, we have given an array of size n, slowly we call the partition, it is reducing the array into 2 sub array, then again we call the partition. So, we have subsequent calls. So, suppose in the first sort we are lucky, in the next sort we will be unlucky. So, alternately we will be lucky unlucky like this sequence, and then we want to see whether eventually we are lucky or not. So, that analysis we will do. So, that means, so now suppose we are lucky. So, this is the lucky recurrence. So, if you are lucky now, then it will be partition the array into 2 equal part, half, and then the recurrence will be 2, but if we are lucky now, next time we know we are going to be unlucky. So that is the unlucky recurrence plus theta of n. So this is corresponding to lucky recurrence. And what is the unlucky recurrence? Now suppose we are unlucky now. If we are unlucky, so that means it is the worst case. So that means it will divide the array into 0 is to n minus 1. So that means our pivot is minimum or maximum from the given input. So in that case the recurrence will be, but now if we are unlucky, then next time we know we will be lucky. So that is why this unlucky means it will be n minus 1 is to 0 or 0 is to n minus 1. So the recurrence will be L of n minus 1 plus theta of n. So this is corresponding to the unlucky recurrence. Okay, so now we want to solve this to get the, so this is 1, this is 2. Now we put this 2 in 1. So that means this will give us what? L of x 2 of. So now we can put L of n by 2 minus 1 plus theta of n by 2. We are just putting this u of n, u of n by 2, u of n is this recurrence. So u of n we are putting just n is equal to n by 2, this plus theta of n. So this will give us basically 2 of L of n by 2 minus 1 plus theta of n. Okay, because this 2 of theta of n by 2 will be combined with the theta of n, and it will together will give us theta of n. So now this minus 1 will play a role of like round upping, I mean lower ceiling or upper ceiling. So this we can easily write as 2 of L of n by 2 plus theta of n. So this is basically our L of n. So recurrence for time complexity. So this will give us a solution order of n log n. So lucky case. So this is lucky. So lucky day. So we are lucky. So this is the observation. This is the observation what? So suppose in the whole sequence of execution. So we have a big array and we are calling the quick sort. So it is partitioning, and then it is dividing into 2 sub array, and again we call the quick sort. In the subsequent step it is further partitioning like this. So in this whole execution, suppose we are 50% lucky, 50% unlucky. So that means if we are lucky, unlucky, lucky, unlucky in this way, then finally our time complexity will be n log n. So finally we are lucky. So this is more intuition that, so if we can ensure that throughout our execution we are good amount of time of iteration, I mean recurrence, we are lucky, then it will give us a lucky case. Okay. So that will give us the idea of randomized quick sort. So if we can, choose the pivot randomly, then I mean then it is there is a chance that the pivot will not be minimum or maximum. So it may be minimum or maximum, but there is a chance that it won't be minimum or maximum. So that way, so it may give us the lucky sequence. So lucky recurrence. So that way it will ensure sort of that eventually we will be lucky. So that we will do in the randomized quick sort. So in the whole sequence of execution, if we can ensure at some number of times of this recurrence is lucky recurrence, then eventually we will be lucky. Okay, so this is one idea behind this randomized version of the quick sort. And another idea is the adversary point of view. So suppose we have a quick sort version and quick sort. So we have corresponding the partition algorithm, partition subroutine. Okay. Now in our partition algorithm we choose the first element as a pivot. Okay. So our partition, our case, we choose So, our case the pivot is AP basically the first element. So, if we have a array starting from P to Q, so our case the pivot is this one X, our partition algorithm. Okay. So, we know the position of the pivot. Suppose we want to take any other position as a pivot, say third element from this array. So, this is the kth element. Suppose we want the kth element, it is not the kth smallest or something, it is the index, kth index. Suppose we want to, so instead of first element, if we want to take third element as a pivot, in general if we want to take kth element as a pivot. So, kth element means kth index. So, AK as a pivot say. Okay. Then we can change our partition algorithm, or we can do what in the initially we will just change this AP and AK, exchange AP and AK, and then we call our original partition algorithm, because now we have exchanged this pivot element in the first element, then we call our original partition algorithm. Anyway, that is that we can do, we can modify the partition algorithm accordingly. So, now we can call the partition algorithm with the index P to Q. Okay. Now, this as a, if we fix the position of the pivot, this as a drawback. Instead of first element, if we fix this third element, if we, this is our say rule, we always choose, this is, we always choose this element as a pivot. Okay. In here we are choosing the kth element. So, if k is 3, this is the pivot. Now, what is the drawback of this? Suppose we design a algorithm, the sorting algorithm, and we give it to the somebody to buy this. So, what that company will do? Company will take this algorithm, and company knows that knows my pivot is the third element. So, the adversary always can construct input where putting third element as a minimum or maximum of the given array. So, we can always do that. So, we put the so we have given array, we put the minimum or maximum in the third position. Okay. Then we call the partition. So, again it will divide into, so if we put minimum, again it will divide into just x will be here, remaining all the n minus 1 element will be here. Again from this, so from this sub array, this is first element, this is second, this is third. Again this will be going to be pivot, again we put the minimum among this array element here. So, this way one can always construct a input where always we are going to choose the pivot as a minimum, or we can choose the maximum. So, that is the drawback. So, if we know beforehand, if we know what will be the position of our pivot, whether first element or third element, then one can always come with an input where by putting the minimum or maximum element in that position always throughout the execution subsequence sub array, then that will perform the worst case. So, that will always give us the 0 is to n minus 1 or n minus 1 is to 0 partition, because that is happen to be a minimum or maximum of that corresponding array or sub array. So, is this clear? So, if we know the, so knowing the position of the pivot is dangerous in that sense. So, we can always come with some input where our code will perform worst case, I mean perform badly. So, to avoid that, the idea of randomized quicksort came. So, randomized quicksort idea is we will not let others know which position we are going to choose as a pivot. So, that will determine at the runtime. So, that is the randomly we choose the pivot element among this element. So, that will save us this type of constructing of this type of input where our code will perform badly. So, that is the idea of randomized quicksort. So, we talk about randomized quicksort. Okay, so idea is to choose the pivot element randomly. So idea is to partition the array, partition around a random element. So we are choosing the pivot randomly. Okay, so we have given a array. This is the array starting from P to Q, say initially it is 1 to n. So any element could be a pivot element, any position. So we just choose a random number k. So this is a set, index set p plus 1 up to q. From this index set we choose a k and k randomly. We generate a random number randomly. So we choose a, so if there are n element, so they are equally likely to come as a pivot element. So this is 1 by n. Okay. So we choose a k. So from this index we choose a k randomly. So this is k and this is going to be our ak is going to our pivot. This is our x and this is a random choice. So before running the code, we do not know which k will be coming. It depends on the random number generator. Maybe this AP can be pivot, maybe AP plus 1, we do not know any one of this. So any one of this element can come with a probability 1 by n if there are n element. So that is the idea. So we choose the pivot randomly from this set at the run time. So before running the code, nobody knows which is going to be the which position, which is going to be the pivot element. So that is why adversary or nobody can come with some input where our code is performing bad, because we do not know which position is going to be pivot. So that is why we cannot put in that position minimum or maximum of that array. Okay. So that is the idea. So we choose the pivot randomly among this set. So we have n element, among this any one of this can participate as a pivot. So that will be decided at the runtime. So runtime we generate a random number, based on that we choose a index and that ak will be the pivot element. Okay. So this is the idea of randomized quick sort. So we can just write a code for that. So you can just quickly write a code rand quick sort. So it is basically a p to q. Okay. So now we earlier version of the quick sort is AP is our pivot element, but here. So again we have the initial condition, if p is equal to q, then done, else what we do, we have to call the partition algorithm and that partition should be random partition. So we call the else, say r is equal to, we will have to explain what is the random partition from a p to q. And even if we want to use our partition, then what we do, we know that our original partition is taking first element as a pivot. Then what we do, we just call this, we choose a k randomly from this set. So we generate a random number, we choose a k from this set and then a k is our pivot. Now we exchange a k with AP, because we know that our partition is basically taking first element as a pivot. Then we call this partition, our original partition algorithm, where first element as a pivot. Okay. And then it will partition into two parts, then we have a that just the remaining call quick sort. So it will partition into two parts. This is the R, X will be sitting here, this is the left subarray, right subarray. Again we have to call the randomized quick sort on both the subarray. And again on this subarray also we have to call a pivot randomly. So that is very important. So in a subsequent step also we choose the pivot randomly. So, again for this survey we have to call a k, we have to generate a random index k, and that will be going to the pivot. So, similarly here. Okay, and the initial call is rand quick sort from A 1 to n. So, this is the code for randomized quick sort. Now, we want to analyze this code. What is the runtime of this? So, to analyze this, we need to take help of random variable, some probability stuff will come. Okay, so what is the time complexity? So, we denote Tn is the runtime of randomized quick sort with n element. Okay. So, then Tn is a random variable basically, Tn is a random variable. Okay, because Tn is will depend on the input pattern. So, that is why it is random variable. So, Tn is basically what? Tn is basically can be written as of the form. So, it depends on the partition. So, if the partition is 0 is to n minus 1, if this is the split, then Tn is T0 plus Tn minus 1 plus theta of n, if this is the split. Otherwise, if T1 plus Tn minus 2 plus theta of n, if the split is n minus 2 dot 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 and dot dot dot, if the split is k is to n minus k minus 1 split, then it is basically Tk plus Tn minus k minus 1 plus theta of n dot dot dot, and this will be up to this n minus 1 plus theta of 0 plus theta of n, if the split is n minus 1 is to 0 split. So, Tn is in this functional form. So, we do not know which partition will occur, we do not know which split will occur, but we know one of the split will occur, any one of this. So, if the random number is bad, then the split will be this. If the random number is very good, then the split will be half half. And so, depending on the random number we are choosing, depending on the pivot element we are choosing, the partition will be one of this, but before running the code we do not know which one will going to occur. Okay, so this is the time complexity, that is why it is a random variable. This is in time complexity in the functional forms. Now we want to make it in algebraic form, so that we can take the expectation. So, to make it in algebraic form, we need to take help of what is called indicator random variable. So, what is that? We will just define xk is 1 if the split is k is to n minus k minus 1, if this is the split, otherwise 0 otherwise. So, xk is the indicator random variable which is 1 if the split is this. Okay. So, one of the split will occur. So, that means one of the xk is 1 and then remaining xk are 0 and corresponding that expression will come. So, that means we can write this functional form in algebraic form like this in terms of this xk. So, Tk can be written as summation of xk into, this is into Tk plus Tn minus k minus 1 plus theta of n. This is xk and k is varying from 0 to n minus 1. Okay. So, this is the expression, that functional form we write in algebraic form, because we want to take the expectation, we want to find the expectation. Now, here we can say the expression. So, now we take the expectation on both sides. So, this is basically expectation of this summation of xk into, this is into tk plus t of n minus k minus 1 plus theta of n. Okay, so this is basically k is 0 to n minus 1. Now expectation is a linear function, we can take the expectation inside. So this is basically summation of x 0 to n minus 1 expectation of xk into this form tk plus t of n minus k minus 1 plus theta of n. Okay. So now if we take this to be independent random variable, this and this. So why from this independentness is coming? So we are choosing the random number for choosing the pivot element. Now every subsequent step we have to choose. So that choice of random number, if they are independent, then we can say this is independent. So if we assume that independentness, then this product can be written as, so if two random number is independent, expectation of w and say y, if they are independent, then we can write as this. So this property is there in the probability theory. So that by that assumption we can write this is k is equal to 0 to n minus 1 expectation of k into expectation of this theta of n. Okay. So now this is basically expectation of, this is a discrete random variable. So expectation of this, so probability of xk equal to 1 is basically 1 by n, because there are n possible split, among this split one of they are equally likely. So this probability is 1 by n. So the expectation and probability of xk equal to 0 is 1 by this. So expectation of xk is basically 1 into 1 by n and 0 into this. So it is basically 1 by n. So this will give us basically 1 by n will come out summation of expected value of this. Now this again we take the expectation inside. So expectation of ek plus expectation of t of n minus k minus 1 plus expectation of theta n. So that is nothing to do with the randomness, that is basically theta n. So this is the term k is equal to 0 to n minus 1. Okay. So if you simplify this, this will give us basically what? So let me rub this. So this will give us we want to show the expectation of Tn is basically n log n. So that is our goal. We want to show this expected value of Tn is n log n, theta of n log n. Okay, so this is basically, now these two term, these two sum, we can take the sum inside. So this is from 0 to n minus 1 and this is from, if we put n is equal to 0, it is n minus 1 to 0. So two term is coming out and this will combine with the theta of 1. So this is basically 2 by n summation of expectation of t of k. K is equal to 0 to n minus 1 plus theta of n. So you got this. Now this first two term we can combine with this. So this can be written as 2 by n summation of k is equal to 2 to n minus 1 expectation of tk theta of n. Why we take 2 to n minus 1? We will use a result which is starting from 2 to n minus 1, and for 0 and 1 this term will be combined with theta of n. Okay. So now, so we got this. Now we want to show this is to be theta of n log n. So for that we have to use some inequality. So that is, we got this. Now we assume this is the substitution method. We prove this using substitution method. So what we are trying to prove? We are trying to prove expectation of Tn is big O of the big theta of n log n. Okay. So now to prove this, we are assuming, so this is a big theta we are proving. So we are assuming this expectation of Tn is less than equal to some a n log n. where a is a constant. So, this is our assumption. So, this is true for k, this we have to prove. So, k and k. So, this is true for all k less than equal to n. So, this we just put it here, and this will be basically give us so this is all less than 2 by n and summation over a k log k plus theta of n. Okay. So, now we will use a result, use this fact. What is this fact? The fact is summation of k log k, k is from 2 to n minus 1, that is why we take 2 to n minus 1 is less than equal to 1 by 2 n square log n base 2 minus 1 by 8 n square. Okay. So, this result we are going to use. So, this result again we can prove by mathematical induction. Summation of k log k. So, if you take this a out, a will be here. So, this is summation of k log k, and this k is starting from 2 to n minus 1. This is basically less than equal to, this is also we can prove by induction 2 by a n, and this is basically half n square log n base 2 minus 1 by 8 n square plus theta of n. So, now we can choose this a such that this will be basically less than equal to a. So, this is a n log n. So, this is true for n. So, we assume this is true for up to n minus 1. Now, we prove that this is true for n. So, this is true for all n. So, basically we prove that the randomized quicksort expected runtime is n log n. But this is expected runtime, this is what is called average case analysis. Okay. This is expected runtime, but worst case runtime is always order of n square, because in the worst case we always choose the pivot in such a way, randomly we are choosing pivot. So, worst case pivot will be always minimum or maximum. So, worst case runtime is always order of n square, whether it is randomized or normal. But if it is randomized version, then expected runtime is order of n log n. So, this is the randomized version of the quicksort, and quicksort is in place sorting algorithm. For quicksort, we are doing everything in the array. We are, for like in merge sort, we are taking an extra array for doing the merge subroutine. For quicksort, we do not need the extra array. So, it is a in place sorting algorithm. Okay, thank you.